Hello, everyone. My name is Yanbo Guo. I am a PhD student in computer science at University of Buffalo, and also I'm a biostatistic intern at Mayo Clinic. Today, I will present you the work I did during my internship, supervised by my advisor, Fei Shen. It is called Building a Computable Heterogeneous Knowledge Resource for Precision Oncology. First of all, what is precision oncology? Different from the traditional cancer treatments such as radiotherapy and chemotherapy, whose main target is the tumor in the body, meaning they are using radiation or special drugs to kill or shrink the tumor in your body. Precision oncology is to develop treatments that target the molecular characteristics of the tumor. It focuses on particular genetic mutations that may cause the growth of the tumor. Because of that, it is crucial to have a knowledge resource that can accurately reveal the explicit and implicit associations between the genes, mutation of the genes, the tumor, and drugs to use. These needs naturally become the motivation for our project. In order to better assist the development of precision oncology, we have the following three goals. First, integrative analysis across different knowledge base, which may provide more and unique information that they cannot provide when used individually. Second, explore semantic associations amongst biomedical entities. And third is to build computable and measurable knowledge base. The knowledge bases and the data set we're using are CIVIC and OncoKB. CIVIC is community-driven open source resource for clinical interpretation of variants in cancer. OncoKB is precision oncology knowledge repository, and both of them can be viewed as a knowledge graph that stores large amount of cancer-related genes, variants of genes, drugs, disease, and their associations. A very important tool must be introduced here to combine two knowledge bases is called Neo4j. Neo4j is a graph database. It stores the data and their connections, making queries and visualization easier than ever. They have a special language called Cypher for querying and building the graph. But you can also install some packages to make other languages like Python or Java to be compatible with Neo4j. As we can see here, CIVIC is giving us around 2,500 nodes and 6,700 edges. OncoKB is providing us 377 nodes and 1916 edges. When we use Neo4j to integrate them together, we end up with 2,808 nodes and 8464 edges. Basically, we took the CSV form data from CIVIC and OncoKB and then used Cypher to convert the data into Neo4j graph knowledge database. So here is a part of the graph database from Neo4j. Different bioentities are denoted in different colors with their names on top of the nodes. So in our particular case, the red nodes represent gene, yellow nodes are variants of gene, blue are disease, pink nodes represent drugs. Also, if you will notice, there are names on the edges, meaning the type of relations between entities. Other than the type, each node and edge may have attributes too, providing all the information you need from a graph database. After building our graph database, we choose to use Node2Vec to get the embeddings for the node, where the embeddings can represent the semantic associations among bioentities to make the knowledge database computable, and measurable. A brief explanation on node-to-vec. It is very similar to word-to-vec. We're not going too mathematical into word-to-vec or node-to-vec in this presentation, but let's just say they believe the words or the nodes in our case that are close to each other should be close in vector space too. As an analogy, the graph would be a corpus in a word-to-vec, and a path in the graph can be seen as a sentence. The node obviously will be seen as word. Let's take a look at this trivial example here. We have a graph. How do we find a path from the graph? Suppose we start from node 1 and do a random walk based on the probability on the edges connecting node 1. We might go to node 4. From node 4, if we do the random walk again, we might go to node 7. And then random walk again, we go back to node 4, and then node 8, so on and so forth. We go to node 12 and 13, and then we got a path from the graph. If we do the random walk multiple times, it will give us enough paths to create the embeddings for the graph. Node-to-vec has two hyperparameters to control how we connect the nodes in a network. More specifically, they control the probability of each edge during random walk. They determine whether we want to associate the nodes more in a breadth-first search way or a depth-first search way. These two hyperparameters are P, the return hyperparameter, and Q, the in-out hyperparameter. The trick here is to find the best set of hyperparameters P and Q so that it gives us the best embeddings we need. Therefore, how do we select the ideal embeddings? We want to introduce two metrics we use to find the best embeddings for precision oncology. The first metric we want to use is link prediction. Link prediction is a very intuitive way of finding the best embeddings for a graph. It is an intrinsic evaluation to find the embeddings that best present the topology structure of the graph. The process is shown on the right-hand side. First, with the node embeddings we got from node-to-vec, we can use such as average or L1 norm or L2 norm to calculate the link embeddings between every two nodes. If the link exists in the graph, the label for that link is 1, otherwise 0. Therefore, we can build a supervised model on top of this and use ROC AUC score or a precision score as metric to see if the prediction is good enough. By tuning the hyperparameters P and Q, we find the set of P and Q that have the best link prediction performance, hence give us the node embeddings. The other metric is to use clustering. We use k-means for clustering. And the idea here is to find the embeddings that can reveal the tight bond between bioentities, especially the implicit ones where you cannot see it from the graph. The evaluation we choose is silhouette score and purity score, since clustering is an unsupervised task. Silhouette score is a measure to see if clusters are well apart from each other and clearly distinguished. Purity score is to see whether the nodes from a cluster is from the same class. We clustered our nodes using their embeddings and choose the embeddings with the highest silhouette score and purity score. It is clustered in high dimensional space, but in order to visualize our clusters, we use t-SNE to project high dimensional data into 2 dimensions. Here are some results we got from link prediction. We have 4 ways to calculate link embeddings from node embeddings. They are hotmart, product, average, L1 norm, L2 norm. As you can see the result, the best node embeddings can give pretty good results of ROC, AUC, and precision, recall, F1 score for all 4 of them. Still, among the 4 different methods, hotmart, product, and average can have the best result. For the clustering part, we have silhouette score and purity score to quantitatively evaluate the results. And we also evaluate the score qualitatively by doing a manual literature review. We detected the disease ESA and the variant of a gene KRAS A146 and docetaxel in cluster 2. After conducting literature reviews, we found that the gene KRAS A146 has a strong association with the disease ESA, and docetaxel is one of the common drugs to treat ESA in practice. Similarly, in cluster 5, we observed that the disease TGFC is associated with gene CDK4. And we also found TGFC could be treated by fluorouracil from the cluster, which is recorded in the PDQ cancer information summaries. So, in summary, what we have achieved in this project are, we built a heterogeneous precision oncology knowledge resource, POKR, integrating unique information from CIVIC and OncoKB. We store POKR in 2 formats. One is Neo4j graph database. The other is the embeddings for computable needs. Third, we facilitate knowledge discovery in precision oncology research. For now, our project only explored the structured information from the knowledge database. In the future, we plan to incorporate edge weights for training based on more clinical professional knowledge as prior. Also, for clustering results, we want to invite more domain experts to conduct qualitative analysis for clustering results to get more practical embeddings. Last but not least, I want to thank my supervisor Fei-Chen Shen for getting me through this project. I also want to thank all the help and hard work from all our co-authors, and also thanks to our fundings for supporting our project. Thank you all for listening to our work. It is my pleasure to present it to you. If there's any further questions or interest about this project, here are the email address to contact us. And here's the GitHub link for all the implementation and detailed results.